Hello everyone, welcome to my calculus lecture. In this lecture, we study continuity. Uh, we're going to talk about the continuity of a function at a point. So here comes the definition. A function f of x is said to be continuous at a point x equals a if the following condition is satisfied. The limit of f of x when x approaches a equals f of a. Remember this property? Okay, in my earlier lectures, when I was talking about the nice limit properties of polynomials, rational functions, sine of x, cosine of x, and so on and so forth, right? I mentioned that they are associated with the notion of continuity, right? So here it is, right? So again, a function f of x is said to be continuous at a point x equals a if limit of f of x when x approaches a equals f of a, right? So when it comes to continuous functions, finding limit is nothing other than plugging in x equals a, okay? By the way, one thing you have to note is that for this condition to make sense, we have to assume the following. So limit of f of x when x approaches a must exist, and also f of a has to exist. In other words, f of x has to be defined at x equals a. So those are the assumptions, right? I didn't write them down, but right, because without them, the expression here, limit of f of x equals f of a, doesn't make sense, right? Okay, so it's actually important to know, what kind of the discontinuities exist. In other words, when f of x fails to be continuous at a point x equals a. So there are actually three types of discontinuities, right? Those are three types actually, obviously came from this definition itself. So first type I want to talk about is what? If f of a is not defined, obviously in this case, the condition, the fails to be satisfied, so the function is not going to be continuous. So here is an example, right? Actually, our familiar example. Let f of x be the function given by x squared minus 4 over x minus 2. Okay? But in this case, f of 2 is not defined, obviously, because what? When x equals 2, you know, the denominator becomes 0, so it is undefined. Okay? However, limit of x squared minus 4 over x minus 2, right? When x to 2, x goes to 2, x approaches 2 equals 4, right? That exists. We did calculate this, right? Okay, by factoring, the x squared minus 4, right? So we did calculate this. So, and also here's, the familiar graph, right? In fact, that's graph of f of x, and you see like what, the white circle, when x equals 2, that means, the f of 2 is not defined, right? Okay. Okay, so next the type is what? The limit of f of x when x approaches a does not exist. Obviously, in this case, f of x is not continuous at x equals a. Okay. By the way, before we go on, what do we mean by actually, the continuous? Okay, so how did we actually end up that kind of, the definition, right? That's something I should have mentioned, all right, earlier. But Intuitively, a function is continuous. Okay, a function is continuous at x equals a means there's no the breakage, right, or there is no hole. Okay, right, uh, on the graph. Okay, on the graph of the given function. So if we go back here, you can see there is actually a hole, right? There is a hole, on the graph, right? So this makes the function not continuous. Okay. And so here in this case, again, type 2 is the case when limit of f of x does not exist at x equals a. So here is an example. Let f of x be the branch function, right? So whenever x is less than or equal to 1, I'm sorry, x is greater than or equal to 1, less than 2, it is defined to be 2x minus 2. When x is greater than or equal to 2, less than or equal to 4, it is defined to be the constant function 3. Okay, in this case, f of 2 is 3, right? Obviously from the definition. So f of 2 is defined, but a limit of f of x when x approaches 2 does not exist. How so? Okay, so to see that, let me go to my notepad. Okay, so the function, the branch function we have is what? F of x equals. So when x is greater than or equal to x less than 2, it is defined to be the line, straight line 2x minus 2. And when x is greater than or equal to 2 and less than or equal to 4, it is defined to be the constant function 3. Okay, so we want to calculate limit f of x when x approaches 2. That's what we want to calculate. Okay, so in this case, the branch point, the branch point, the branch point of this function is actually 2, as you can see, right? So at 2, it's like a tree branch, right? So the function is f of x is separated when x equals 2 into the two different functions, right? So because of that, we will have to actually calculate limit, in this case what? Right hand limit, left hand limit separately. So first, let us talk about left hand limit. So limit of f of x when x approaches 2 from the left side. In other words, the x is approaching 2, but those are the x values that are approaching 2, approaching the number 2 are less than 2, right? Less than 2. So in this case, when x is less than 2, what is that? The function is 2x minus 2. So we replace f of x by 2x minus 2. So when x approaches 2, 2x minus 2 are going to 4 minus 2, which is 2, right? And limit x approaches 2 from the right, okay? So right hand limit. So those x values are greater than 2, okay, while getting close to 2. So when x is greater than 2, from this definition, it's got to be 3. So we replace f of x by 3. 3 is constant function. So no matter what, how x is approaching, where to where like x is approaching, nothing changes. It's still 3. So what do we have here? The left-hand limit, right-hand limit, these are not the same. Okay, these are not the same. So limit of f of x when x approaches 2 does not exist. Okay, does not exist. So when this happens, as you can see from the graph, this is the graph of actually, our branch function, right? As you can see, the limit does not exist, and what happens? You see a breakage, right? We see a separation, breakage of the graph, right? So that makes what the function discontinuous, not continuous. Okay, so last type of discontinuity is the following. Okay, the f of a is defined, and also the limit exists when x approaches a, but they do not coincide. Okay, so when that happens, also, the function fails to be continuous at x equals a. So here is an example. Okay, let f of x be uh, x squared minus 4 over x minus 2 when x is not equal to 2. But when x equals to 2, it is defined to be 3, right? Okay? Then f of 2 is by definition, of course, 3, but limit is 4. So they do not coincide, right? As you can see here, we see also, the separation of, the graph, right? So that's what makes the function not continuous. Okay, do you remember, those nice properties of, limits, like limit of f plus limit of g? Actually, I better write down. Okay, so let me uh, go to my notepad. These properties. So limit f of x plus g of x. Actually, the same goes for also minus as well when x approaches a. So that's limit f of x when x approaches a plus or minus limit g of x when x approaches a, right? And also like a limit of c times f of x, c being a constant, right? In that case, this constant can be brought outside of limit, okay? Limit of f of x, x approaches a, okay? And limit f of x times g of x when x approaches a, that's the limit of f of x times limit of g of x. Of course, in this case, the assumption is that both the limit of f of x, limit of g of x, they both exist, right? And also last one was the limit of f of x over g of x when x approaches a, that equal to limit of f of x over limit of g of x, okay? When x approaches a, x approaches a, here in this case, that this is true provided limit of g of x when x approaches a is not equal to 0, right? Okay, so these are the nice properties we studied before. Using these properties, we can show the following, okay? properties of continuous functions, right? So continuity is defined by limits. So, we have the following theorem. If functions f of x and g of x are continuous at x equals a, then the following uh, statements are true. F plus or minus g of x, okay, which is the same as f of x plus or minus g of x, right? That's what the definition of this function here is continuous also at x equals a. And f times g of x, which is defined by f of x times g of x, is also continuous at x equals a, right? And the f of g over x, which is defined by this guy here, is continuous at x equals a, provided g of a is not equal to 0. And I didn't write it down, but obviously also we can say c times f of x, right? If f of x is continuous, then the constant times that function is still continuous. Okay, right. Okay, so let us talk about next some important classes of continuous functions. We talked about this already, but every polynomial p of x is continuous everywhere. Okay, everywhere means that for any the real number a, the p of x is continuous at x equals a. Okay, because as we have seen in my earlier lecture, the polynomials satisfy the continuity condition, right? Okay. Likewise, every rational function p of x over q of x is continuous wherever it is defined, right? In other words, where except those x values that make the denominator 0, right? It is always continuous. And sine of x, cosine of x, they are continuous also everywhere. Tangent of x is continuous where it is defined. Okay, so remember, the tangent of x is defined everywhere except at x equals plus or minus pi over 2, plus or minus 3 pi over 2, plus or minus 5 pi over 2, plus or minus 7 pi over 2, and so on and so forth. Because at those points, cosine becomes 0, so the tangent of x is not defined, right? So other than those points, right, tangent of x is continuous. And also, if n is a positive odd integer, y equals nth root of x is also continuous everywhere, okay? But what if n is a positive even integer? In that case, y equals, nth root of x, for instance, like square root of x, right? As we know, is defined on, the, what is that? 0 to infinity, okay? In other words, we know that when n is an even positive integer, right? Nth root is defined only for non-negative numbers, right? That's why. Okay, now here's another important thing about the continuous functions. So what if we compose, right? So we compose two continuous functions. Okay, so what happens to the composite function? It turns out that the composite function of a continuous function, two continuous functions, is also continuous. So here's the theorem. Suppose that limit of f of x when x approaches a equals L exists, right? Equals L, so as a number L, it exists, and g of x is continuous at the number L. Then what happens is limit of this composite function, which is actually defined by g of f of x, right? Okay, that equals g of limit of f of x when x approaches a. Okay? Now, using this property, this is very important property by itself, but then also, it leads to the following corollary. If f of x is continuous at x equals a and g of x is continuous at f of a, then the composite function, f, so this is how you read it. F followed by g, f followed by g of x is continuous at x equals a. In other words, the composite function of two continuous functions is again a continuous function, as I mentioned, okay, earlier. So here's an example. The function y equals square root of x squared minus 1 is actually a composite function. F, the f followed by g of x, okay, f followed by g of x of two functions. F of x is square root of x squared, x squared minus 1, and g of x equals square root of x. In this case, f of x is continuous everywhere, and g of x is square root of x, right, is continuous on this interval, right, from 0 to infinity, all right. So the composite function f followed by g, f followed by g of x, which is given by square root of x squared minus 1, is continuous on the following interval, okay, the following interval from negative infinity to negative 1, union 1 to infinity. Okay, that's going to be the domain for this composite function. By the way, notice that this y equals square root of x squared minus 1 is a part of the parabola. The parabola x squared minus 1, x squared minus y squared equals 1, where y is greater than or equal to 0. Okay? So its graph is going to be so the graph of a hyperbola, right? Hyperbola x squared minus y squared. Right? So the graph, so here's a negative 1 and 1, okay? So the graph goes like this. Yeah, yeah, it's actually difficult for me to sketch graph because, writing, actually drawing on my notepad, it's slippery, okay? It's slippery, so, you know, it requires some effort. But anyway, it looks like this, okay? So that's like a shape of, a hyperbola, right? Okay? But, the y equals square root of 1 minus x squared as a part of this hyperbola when y is greater than or equal to 0. So really, like, we are talking about only the part above the x-axis, right? So we are actually talking about only this portion. So that's the graph of it. So the line in red, that's the graph of it, y equals square root of negative x squared. And as also we see the domain is negative infinity to negative 1, okay, and 1 to infinity, right? So that's where this is defined. Okay, so going back to my lecture slide. The continuous functions also have, the many, the nice properties. Okay, so one important property is something called the max-min theorem. So what is that? So here's the theorem. Okay, it is named max-min theorem. If f of x is a continuous function on a closed interval AB, that's important by the way, closed interval AB, okay, that's the domain, then f of x attains in its uh, f of x attains its maximum and also its minimum values on the closed interval AB. Okay, so in other words, you can always find the maximum value of f of x and the minimum value of f of x on the interval, closed interval a b. That's very important. In general, it is not true. Not necessarily you can find the maximum or minimum value of a function in an interval. However, for continuous function, also the interval plays an important role. Closed interval, okay, so f of x is a continuous function on a closed interval, then, you know, f of x is guaranteed to have its maximum value and minimum value on that interval. Okay, so that's Max-Min theorem. Very important. Okay. Another important property, right, that I want to draw your attention is something called the intermediate value theorem. It is abbreviated to IVT. So here's the theorem. If f of x is continuous on a closed interval AB and f of a is not the same as f of b, so f of x have different values at the end points of the closed interval. In that case, f of x takes on every value between f of a and f of b. So what does that mean? What it means is the following. Okay, so maybe that like a picture might help you to understand. Okay, so here I'm gonna draw a picture. So here's a closed interval. Okay, so here's closed interval AB. Okay, so f of a is so let's say that like here's f of a, and so f of b is here, right? So so this is a f of b. The so the function f of x is a continuous function, right? So without a hole or a breakage, right? So that the graph has to be nicely connected. We don't know how it is connected, okay? But it is nicely connected. No holes, no breakages, right? Okay, so that's what happens. In this case, you pick, so any number here, you pick any number here, right? So let's say like k between f of a and f of b. So you can always find a value c, right, between a and b such that f of c is k, right? That's obvious from the picture, right? So So, the f of x can, takes on like any value between these two means the following. So for any number k between f of a, so here assumption is f of a is smaller than f of b, obviously, right? So, uh, there exists some number c between a and b such that f of c equals k. So that's what it means, okay? That's intermediate value theorem. Now also you can see that like, the name, intermediate value theorem makes sense, right? Okay, so for this reason. So that's very important property. And going back to our my lecture slides, right? And this theorem leads to an important corollary. If f of x is continuous on a closed interval, same condition, and f of a times f of b is less than 0, okay, less than 0. So what it means is that f of a and f of b have different signs, right? In this case, f of x equals 0 for some x between a and b. This is actually just a special case of the previous intermediate value theorem, which can be also easily understood if you draw a picture. Okay, so let us visualize, what's going on. Okay. So I'm going to draw a picture again. So here's let's say here's a interval, closed interval a and b. So let's say f of a is a negative number, right? So, let's say that this is a f of a, and f of b is some positive number. So that's f of b, okay? So, again, f of x is a continuous function, so it has to be nicely connected, right? Without a whole or a breakage, right? Something like that. So, in this case, 0, it has to cross the x-axis. So, the what is it? 0 is the value between f of a and f of b. Now, obviously, by the intermediate value theorem, right? So in this case, by the intermediate value theorem, we see that there exists, right, x between a and b, right, such that f of x equals 0. Okay? So why this corollary? Well, that's fine. Okay, great. You know, but what's the big deal about this corollary? Actually, it is a big deal. This corollary can be used to see if the equation f of x equals 0 has a root, a solution, right, in some interval. That's important, okay? Because there are lots of the difficult equations, right? So they say, for instance, like a linear equation or quadratic equation, no problem. You can easily solve them. But there are like what cubic equation, quartic equation, quantic equation, and so on and so forth. These are they're very difficult to solve. Not only that, we have also equation. We could have equations involving like trigonometric functions and so on and so forth. They can be also difficult to solve. So wire, it's we may not be able to find the exact solutions, right? Okay. There are like ways to solve it. For instance, there is method called the Newton's method that allows us to find the approximation to the root of the to a root of the given equation. But in order to use Newton's method, okay, Newton's method, you will have to at least know the root, where the root is located, okay? So to see that, what we can use is this corollary, okay? So this corollary is important, okay? For that application. All right, so here's an example. Show that the equation x cubed minus x minus 1 equals 0 has a root in the interval -1, 2. Okay? Right. So let me go to my notepad. So we have, so we want to see, so we want to show, right? We want to show that the equation x cubed minus x minus 1 equals 0 has a root on the interval, on the closed interval, -1, it was -1, right? Yes. Two. Okay. So how do we use the corollary to show this? First, let f of x be the following function: x cubed minus x minus 1. Okay. And then we are going to calculate the value of f of x at each endpoint, right? So first, the f of -1. So that's -1 cubed minus 1, minus -1, -1. So what do you have here? That's -1, +1, so they cancel each other, leaving only -1. F of 2 equals 2 cubed minus 2 minus 1. 2 cubed equals 8, so 8 minus 3, that's going to be 5. So what you see, these two guys have different signs, right? One is negative, one is positive. So f of -1 times f of 2, that's negative. So it does satisfy the conditions for the corollary, right? F of x is continuous. I mean, this is a polynomial, so of course continuous everywhere. So, on the closed interval, -1 to 2, obviously, it is continuous, right? And also, the f of -1 times f of -2 is negative, so they have different signs. So in that case, we see that by the last corollary, right? The corollary. There exists x between -1 and 2 such that f of x equals 0. In other words, x cubed minus x minus 1 equals 0. So we don't know what the root is. We don't know what it is. So right. So we don't know what the root is exactly, but at least by this corollary, actually the intermediate value theorem, we know that at least there is a root x between -1 and 2. So inside this closed interval. Okay. All right, so that is it. And more details of my discussion in this lecture can be found in my lecture note at the following address. Okay. As usual, I made a hyperlink, so you don't actually have to, copy and paste or, type this address to get to the note. You just have to click on it. And also, if you want to visit my, the main uh, blogger site where you can find also, my other lecture notes, you just click on this blogger, right? Which is hyperlinked as well. Okay, so thank you for watching. Thank you for listening. I'll see you next time. Bye bye.